Let's look at a little example where we can see this space-time distance or this space-time interval in action. So let's imagine that we have a rocket that's being viewed from the Earth, and it's traveling at a constant velocity, we're told, for 13 years. From the perspective of those on Earth, it covers a distance of 5 light years. We want to know how many years pass on the ship's clock. You can solve this problem simply by calculating gamma using the time dilation formula. Straightforward to do. Let me just show you the alternate approach that you could follow that makes use of this space-time invariant. How does that go? Well, let's look from the perspective of the Earth frame. What is the data that we are given? So we are told that delta t is equal to 13 years from the perspective of those folks on Earth. We're told that delta x is equal to 5 light years. And again, this is all in the Earth frame. And we want to work out what's happening in the rocket ship frame. Now, in the rocket ship frame, that frame moves with the ship itself. So what that means is that delta x prime is equal to 0 in that frame. And we're asked to figure out what delta t prime is. And now we can do that by making use of the invariant space-time interval. So we just calculate away minus c squared delta t squared plus delta x squared. We'll put numbers in there for a moment. But the conceptual idea is that this thing is equal to minus c squared delta t prime squared plus delta x prime squared. And since delta x prime is equal to 0 in the rocket frame, since the frame moves with the rocket, this gives us c squared times delta prime squared. We know delta t, we know delta x from the data that we're given in the problem. Therefore, now we can solve for delta t prime. So now it's just a matter of plugging in some of the numbers. And what you will therefore get here is c squared times delta t. We know, again, if you c equals 1 light year per year, to make life simple, then this 13 years turns into 13 light years. If you square that, that will be minus 169 light years plus 5 squared light years, so plus 25, equals 144 times light years squared. And that's supposed to be equal to, I should put a minus sign there. That's supposed to be equal to minus c squared times delta t prime squared. And of course, that means that delta t prime is equal to 12 years. So it's just a little example where you can see the space-time interval come into its own. And the nice thing is we're able to calculate that result without having to calculate gamma. We just made use of the invariance of the space-time interval to get at the answer. So that gives you some feel for the way in which you can make use of this invariance. To get a better feel for it, you should play around with this little demonstration where you can see how it doesn't change as you change reference frames. So we just did an example of that. But let's take a look at an example over here. So in this demonstration, you get to pick the space-time coordinates of some chosen event. Choose them at random if you'd like. And then let's vary the speeds between the two frames. And look, all of the coordinates, t prime, x prime, are varying as we mess things around here. But the value of the interval between them, this number over here, is not changing at all. So look way over there on the right-hand side. These numbers are rapidly changing, but the interval itself stays fixed. So that is a demonstration of the invariance of the space-time interval as you change from one frame to another. We've given an example of how to put this invariance into practice to solve problems in a somewhat different way.